Okay, this is lesson 8.3c. We're going to be using geometric sequences and partial sums to solve some problems that don't really look like geometric sequences. In this lesson, you will write repeating decimals as fractions. We'll solve annuity problems compounded by period and continuously. Okay. Let's look at this problem right here. Consider this decimal, this repeating decimal. The part that repeats is the 135. Okay, so let's look at this in parts. We have the 0.135 repeating is this 0.135 plus another 0.135 after the first 135, and then another 135 after the second 135, so on. So writing these as fractions, I have this, or we can see that we're actually multiplying by 1 over 1,000 each time. So that's going to be my R. Okay, so the first term is 135 over 1,000, and R is going to be 1 over 1,000 because these reduce. And we get 1 over 1,000. Hope that makes sense. Then we can use this, right? We have the first term, and then we have R. And 1,000 over 1,000 minus 1 over 1,000 is 999 over 1,000. And the 1 over that means reciprocal, so we really have to put the 1,000 on top. Cancel the thousands, and we get 135 over 99. A lot of people think this is too confusing, so I offer you a shortcut where we don't use the formula, but we just use an algorithm. So we know that, oh, by the way, this reduces, the 135 over 999 reduces to 5 over 37. 0.2 repeating is equal to 2 over 9. So this 9 makes this repeat. So how can we make this repeat? Well, we can just put that over 999. So that's how we get to here, and then we just reduce, and we can bypass all these steps. Okay? Just realize that this is really done this way because if you don't remember the rule, you can always use your summation for a geometric sequence. So how would you do this one? The 678 is the part that repeats. We're going to put 678 over 999, and it can be reduced. You need to reduce, and in this case reduces by 3. That's how we get the answer. One more. Let's see if you can do this one. All right, 67 is the part that repeats. 67 over 99. And that does not reduce, so we're done. Okay. Well, you say that must be too good to be true, and it kind of is, because we don't always have the whole thing repeating, so you have to be real careful here, because this 2 doesn't repeat. So this is really 0.2 with a repeating bar over on the 47. Well, you can't put this over 999 because that would just make the whole thing repeat. It will make the 2 repeat also. This is not the pattern that you want. We're going to separate out that 2. Okay, and we're going to have the rest of it that repeats. And you can go through the long way using the summation. Okay, just leave the 0.2 in the front, or 2/10, and then you're going to figure out the part that repeats. You're doing the same thing, except this time it'll be 1 over 100. And then doing all the same steps as before. Okay. And then you'll get this. All right, and 99 times 2 is and then adding that all together with the common denominator and reducing, you'll get 49 over 198. Now, let me offer you a shortcut or a little amendment to that shortcut that I gave you. Okay, notice that it's just a 0. All right. Okay, let me show you what I mean. You're going to take that 0.2, the 2/10 out, separate the non-repeating part with the repeating part, like I did in the last slide, except you're going to do this as 9 over 9s. But because we only have 2 digits over 9, so we got just over 99. But we have to have this space here, the 0 here, so we're going to add a 0 to the 99, so it'll be 990. Now this 0, I'm just showing you to match this, but this 0 doesn't matter. We don't have to put a 0 in front of a number. But if we put a 0 in behind a number, we actually make that number bigger. But when we put a 0 in front of a number, it doesn't do anything. Okay, so now we add these together. Well, in order to add these together, I need a common denominator, and that would be 990. So I multiply the numerator and denominator of the 2/10 by 99. I get 990. And 99 times 2 is 198. Now I have a common denominator. Add my numerators. I get 245. 245 over 990, that reduces by 5, and that's 449 over 198. Okay, see if you can do one. Okay. How would you write that as a repeating decimal? Okay, writing that in with a bar notation, we have 3.8. That part doesn't repeat, and then a repeating bar over the 2. Separate the part out that's not repeating is the 3.8, and the part that repeats is 0.0. Then the 2 repeats. Don't draw the line over the 0,2 because then it'll be 0,20202, right? Okay, so 3.8 is 38 over 10. Leave a space, so that means we add a 0 to the 9. And the common denominator is 90, so multiply the numerator and denominator by 9. And I got 342 over 90 plus 2 over 90. Adding the numerators together, I get 344. Reducing that by 2, I get 172 over 45. Okay. So what is 0.3 repeating? That would be 3/9, which reduces to 1/3. What is 0.33 repeating? That is actually the same as that one, right? Because it doesn't matter how many 3's you write down. So that would be 33 over 99, which is still 1/3. Reduces by 33, 11 and 3. What about the 0.2 repeating? That's just 2 over 9. What about 0.321 repeating? That's just 321 over 99, reduces by 3, 107 over 33. What about 0.3 repeating 21? That will be 3/10 plus 21 over 990. Getting a common denominator, and we're going to add those together and reducing, we'll get 53 over 165. What about 0.321 repeating? Well, if the 0.32 is the part that doesn't repeat, non-repeating, put that over 100 to get the decimal here. And then that'll be 1 over 9, and we want 2 spaces over before it repeats, so we add 2 zeros to the 9. That's 900. In a common denominator and adding, we get 289 over 900. Okay, just refresh your memory on compounding formulas. This is PERT, this is compounded by period. And knowing what you know about the geometric sequences, know what's inside the parentheses or what's the base of the exponent is going to be your common ratio. That's not the same R as your interest. 1 plus R over N is your R for your geometric sequence, the common ratio. And P would be the principal, and in that formula would be the first term, A1. Okay. So just make sure all these are in the same units. This is going to be interest rate per year, compounds per year, and time is in years. They all have to match, otherwise the answer is not going to come out right. Okay, let's get started with an annuity. Annuity is a real life interest problem, money problem, and it just means that you're going to either pay in little bits at a time to get some reward out at the end, or a reverse annuity is if you had a big chunk of money. Let's say your grandfather leaves you, your great grandfather leaves you some money in some kind of a trust account, some amount like $1 million. And a reverse annuity is you can take chunks of it out until it's all gone. Okay, you either build it up by putting money in a little bit at a time, or to build up one big balance, or you can put in one big balance and take out one little chunks at a time until it's all gone. So that's what an annuity is. So how do we set up this problem? Well, we're going to use this compounding formula because we know that we're compounding by month. And setting this up, P, the principal, R, the interest rate, N, the number of periods per year, time, and the amount that you're going to have at the end, your balance. That's what they're asking for. So in this problem, the principal is $50. The rate is 0.06 per year. N is 12 months per year. And then time is 2 years. Make sure all these have the same units on them, otherwise they don't work. If you put N is 1 time per month, then you realize that this is not going to work out. Or if you put 24 months, then this will also not work out. And A is the unknown. That's what you're trying to find. Now, the tricky part about this problem is your first term, your first $50 that you put in, it's actually going to make you the most money because it sits in there the longest. Your first $50 is going to sit in there for 24 months, whereas the last $50 you put in there is only going to sit in there for 1 month in your account. So the first month is A24. It's actually the one that's going to be in the annuity the longest. It's going to be in there for 24 months. So using this formula, the principal is 50. 1 plus interest rate is 0.06. Since it's compounded monthly, we have to divide that by 12 times per month. And then we have 12 months, that's N, times 2 years. So that's how we get our first payment, how much money we're going to get from our first payment, the first deposit in there. The first deposit is going to be in there for 12 months, and we're going to get $56.36 approximately, rounded to the whole penny. So if you put $50 in after 2 years, you can get an interest of $6.36 added to your $50, so you really have $56.36. Likewise, the second payment will just be in there for 23 months, so you have to reduce this number here by 23, right? After 1 month goes by, you put in another $50, so that second $50 is going to only sit in there for 23 months before you take it all out after 2 years. The second payment that you put in there is actually worth $56.08, or $6.08 in interest, plus your 50. So as long as you get the last payment, the one that's been sitting in there for only 1 month, is 50 times 1.005, which is all of this here. Okay, all of this here. Now that's really the common ratio of your geometric sequence. That's going to be in there for 1 month. Compounding formula, this formula here, or the summation formula. So you got 50 times 1.005, 1 minus r to the n, which is 24, and 1 minus r, and r is 1.005. That's this, or 1 plus 0.06 divided by 12. Okay, and finishing this on your calculator, you'll get $1,277.96 after 2 years of putting $50 in per month. This is a good way to save some money. Okay, you try one. A deposit of $100 is made on the first day of each month in a savings account that pays 6% compound monthly. What is the balance at the end of 4 years? So you should have all the notes from the last problem I did, and it's the same problem, so you should be able to come up with the answer if you want to try this and learn something, okay? So setting this up, the principal is 100, R is 0.06 per year, N is 12 times per year, and T is 4 years, and A is what you're trying to find. So all we care about is the last payment we put in there, or A1, and that'll be 1 times 1 plus 0.06 over 12 to the 1 power. And from the last problem, we know that this is going to be 1.005. Okay, so that's my A1. So using the summation formula, we can put this together, and the sum of 48 months is equal to the first one times 1 minus 1.005, the 48 months over 1 minus 1.005. It comes out to $5,436.83.